Okay, welcome to my presentation. Just give me time, one slide to introduce my company. Here you see my team. Just recently I had a talk with a business partner and he said, oh, he doesn't like to see team pictures and whatever. To me, this is the most important part of MST Vision is my team. I have a young team of 15 people doing an amazing job. You will see in the next slides what we can do. So it's very important that you know who we are. We provide integrated components. The new one, which I will show you in the presentation, we do a lot of development services. So we help our customers to solve their problems. We do a lot of consulting and training. And you see, we are only 15 people, but for 15 people, we have quite a cool technology stack. So we are able to balance the load between CPU, FPGA, and GPU. When it comes to CPU, we do most of the time use Helken. So we are a VTech certified education partner. To be honest, I love Helken. I teach Helken in university. That's what we're trying to do in all the projects where the CPU is involved. When the CPU is not fast enough, we go to the FPGA using Basler's hardware, formerly known as silicon software. They have an integrated development environment called Visual Applets, and we can do really cool things you will see in the next slides. And like everyone else, we are also using GPU to do artificial intelligence projects, but not only AI things. What makes us different is we combine high-end technology, creativity, and we just try things where many others fail. Just examples. 4 years ago, we have been like only 4 or 5 people. We have been contacted to develop a sorting technology, a sorting system. And there was nothing available which fitted the requirements of this customer, so we developed it by our own hardware. We used the Basler frame grabber with the FPGA, and at the end we came up with a solution. We can control up to 1,000 actuators per frame grabber at high frequency, so we are able to sort 1 million objects a second, if the algorithm is easy, to be honest. If you want to see this, come to our booth, and you will see 2 demos showing the high-speed sorting. Second example, we always try to do something different than others. We had a customer contacting us, and he has a foil, a film, which needs to be sterile. And these guys are so scared that something like an insect is flying into his line, and his day of production is completely blocked. But the problem of him was, he has a print, and he has the problem to separate on CPU software the print which is desired from the undesired contamination. And it was really high speed, big problem, so we came up with photometric stereo. The customer doesn't want to have his picture here, so we created this fake picture. And to show the principle, we printed our logo flat on black on white on paper, and we printed the image of the insect flat on paper. And on top, we added 3 insects, real insects. And in the upper image, it's quite difficult to separate the real ones from the fake ones. But in the lower image, it's so easy. It's really easy to detect the real insects. So we try to move complexity somewhere else so the CPU can do the job. That's why we love to do CPU, FPGA, and GPU. Coming to our technologies. One of the base technologies we are using, we call it multi-channel. We love line scan cameras, and we are really happy that now there are more cameras coming up because in, let's say, 3 years ago, nobody wanted to talk about line scan cameras. It's improving a lot. That's what we like. We have developed this technology, I think, 14 years ago. It's time division multiplexing of different illuminations. So you have one single line scan camera, and your object passes only one time under the camera, and we can flash up to 10 different illuminations. It can be bright field, dark field, reflective mode, as you can see here. Your camera needs to cover the speed. So if you want to have 3 illuminations like here, your camera needs to be able to run 3 times the speed. Everything is done by the frame grabber, so you don't need to handle anything. It's very easy to integrate. It's just JNICAM interface. And there's no offset between the lines, so merging of data is much easier compared if you have like 3 different cameras. And we even check for missing lines if some trigger is lost. We can acquire any bandwidth your camera or frame grabber can provide, like CXP or camera link. But in the moment, for sure, we prefer CXP. What is the key advantage? It's the more properties or features you can calculate or capture from any surface or defect, the better your inspection system can become. So that's why we like it. And important, this applies to rule-based standard algorithms as well as on any AI solution. Guys, we are working on industrial image processing. Image is the core. So we always start at the image. And you can see here we can do a multi-angle like bright field, dark field, reflective mode. We can have different wavelengths for multispectral applications. We do a lot of photometric stereo, also known as shape-from shading, structured light. You can design anything you like when you light, what you like, anything you light, and your camera is compatible to our technology. You see a lot of examples here. Check it later afterwards. Now coming to photometric stereo, which is another technology which we like. Photometric stereo, for those who are not familiar with it, helps you to separate topography features from texture features. Like the former killer application was the prial dot. You need to read 100% of the prial dot, but you also need to read the text. So it's texture mixed with 3D curvature events on the surface. And using photometric stereo, you need to acquire at least 3 images of the same scenery. We take always 4, with 4 different illumination directions, and then you can calculate these images. Since we love line scan, we did already since many years the acquisition of line scan images doing this. We love to work with lights from the company MTD, because in our market, in the high-end business, it's the best light we know. The portfolio fits perfectly our strategy. But it's a challenge to do high-speed line scan applications. And at the time we started, the CPU was by far not capable running the speed. So what did we do? If the CPU cannot do the job, we bring the algorithm to the FPGA. So these images are acquired by the FPGA, and also the algorithm is executed within the FPGA. So you obtain these images without any CPU load, just via JNICAM interface. We even compensate for movement, but this is only detail for someone who is really deep into photometric stereo. We even compensate this one. Showing you one of the examples, it's the battery foil. Here you see our standard setup, which we use in lab. We acquire 3 standard lights like reflection, backlight for pinholes, or dark field for anything on the surface. We acquire the 4 images needed for photometric stereo, and we calculate 4 more images. The curvature, the X image, Y image, and albedo. All of this without CPU load. Each image 16K, which makes the overall image 176K wide. It's really huge images. And the biggest problem our customers have, still if the CPU is not involved, they have trouble afterwards processing all these images. Even having the best lights we know in our high-end market, the speed customers ask us was not possible because the light was still not fast enough. So at MST Vision, what do? If something is not available, we try to develop something new. So here you see our new product, which is just recently finished the development. It's our photometric stereo line scan solution. It's the overall setup, and the core of the system is a new light. We call it the photometric stereo line light. It's a line light perfectly optimized to photometric stereo. Actually, it's 4 line lights in 2 housings in 1 mechanical unit. And to obtain proper photometric stereo images, you need a strong angle of, let's say, up to 60 degrees. We typically choose 35 because it's a good compromise in our optical setup, because you tilt it in one direction to 35, also in the other direction to 35, so the angle which is needed for photometric stereo comes up to be 45. Due to our internal design, we can space the LEDs very close to each other, so we have a lot of LEDs per length. They have a small opening angle in one direction, so it's giving a better result in photometric stereo. And we focus the light to have a narrow line width. And with all these tricks combined with the really fast driver which we have developed, we obtained a surprisingly high brightness. Honestly, we have been surprised by ourselves. It was not expected to be like this. We are able to obtain 3 kilowatts per square meter per channel. And we can switch on and off in less than 1 microsecond. Here you see the rise and fall time of the light. It's one mechanical unit which you can integrate. And this brings me to the next slide. What are the advantages for integrators? Because we are aiming for integrators. First of all, how to integrate it? It's just one standard software interface doing all the job. Camera, parameters, image acquisition, setting the timing. So if you are used to GenaCam, that's all you need. You just install the Basler grabber and you're done. You need to connect power to the light and one single trigger cable coming from the trigger board connected to one light, controlling all the 4 channels. Nothing else to do. It's one mechanical unit, so no complex adjustment needed. You can add easily additional illuminations like backlight or reflective channel or different wavelengths, whatever you like. And our new FPGA design can handle up to 3.6 gigabytes a second. Again, without CPU load. It's scalable in master-slave, so first grabber is the master grabber, and you can have several slave grabbers in the same PC or in different PCs, because all need to be synced to be able to have the photometric stereo image on really large scale. So we don't care about length, because you just add cameras, but you need to be able to process the data, which is really a challenge. At our booth, you see the demo. It's the Basler Racer 2 8K camera running at 200 kilohertz on a lithium-ion battery foil at 25 micrometer resolution. So we are able to go 75 meters a minute on photometric stereo, which at least I don't know any other system can do. So I have no idea how to name it, but I don't know any system which is as fast as this. And small teaser for a future project, because I mentioned we do CPU, so if we do something a little bit slower, we use Helken to calculate the images. If it's really high speed, we go to FPGA, but it's a special technology, and in between there was a gap. So we filled the gap with a GPU-based photometric stereo. It's no library, it's no FPGA programming, it's just a GPU-based software which we have created. The reason why is that some of our customers need the height map. Based on the X and Y image, you can integrate the slopes coming up of the height map, and the FPGA doesn't like large filter kernels which are needed, so we use the GPU for the height map calculation. And since the GPU is doing the height map, it was very easy also to add the photometric stereo to the GPU. We can process roughly 500 megabytes a second, can be used for area or line scan camera. The plan is to have easy software integration, again using GenTL. Setup can be tailored to your needs. Come to our booth and you will see the demo. A Baumer 10 gig E camera running with the new RDMA feature with the Helken interface. Yeah. The camera is controlling the illuminations, and again we calculate all the images in the GPU. That's all from my side. Thanks for your attention. see us at booth 10B38. And now I'm happy to answer questions if we still have time.
We still have time. Perfect. Questions from the audience? Yes, please.
Hello. Could you introduce more about the multi-channels? How did you configure the multi-channel with a 3-camera or frame grabber or a single camera with a multi-strobing?
Sorry, can you repeat? It was tough to understand.
I would like to know how did you configure the multi-channel system? You mentioned that the one single camera and there's a lot of illumination and the frame grabber reformation the images. So you can acquire 3 images, different wavelengths. So could you tell me how did you configure the hardware?
Yeah. So it's the standard frame grabber for Basler where we add our special features. The frame grabber has 10 outputs, so you can connect 10 lights, which needs to have a fast trigger input. We acquire the lines, and the frame grabber is line 1. LED 1 triggered, line 2, LED 2 triggered, and then we have this mixed data stream, and it's rearranged in the frame grabber. So the frame grabber is the core component doing all the job. No external controller if your light is capable to being triggered. It's any line scan camera which is compatible to CXP or camera link. So it needs to be compatible to Basler grabbers.
One more thing. So how did you many camera you use? With a single camera, you made a multi-channel?
Sorry, it was really tough to understand.
I want to know how did you many camera you use to make a multi-channel system?
No, it's always done by the frame grabbers. Sorry, I'm not sure if I did the question correct, but it's the frame grabber doing all the job. And if you want to have more than one camera, they are synchronized. And the master grabber is doing the timing, and the slave cameras need to follow precisely the timing, and we synchronize electrically master and slave frame grabber. Maybe we discuss afterwards. I'm happy to talk to you face to face.